This is Yogesh Landey, and in this video, we will see our numerical based on the counterflow heat exchangers to find out what is the number of tubes required for a given conditions. Let's see the statement of this one. A steam enters a counterflow heat exchanger, a dry saturated at 10 bar and leaves at 350 degrees Celsius. The mass flow rate of the steam is 720 kg per minute. The hot gas enters the exchanger at 650 degrees Celsius with a mass flow rate of 1320 kg per minute. If the tubes are 30 mm in diameter and 3 meter long, determine the number of tubes required. Neglect the resistance offered by metallic tubes, and the data is mentioned that are for a steam, T saturated is 180 degrees Celsius. Specific heat of the steam is 2.71 kJ per kg Kelvin. H1 for the steam, that is heat transfer coefficient for a steam, is 600 watt per meter square Kelvin. For the gas, specific heat is 1 kilojoule per kg per Kelvin, and the heat transfer coefficient for the gas, that is outside one, is the 250 watt per meter square Kelvin. Now, this is a numerical that the steam is entered into the heat exchanger, and there is an exchange of heat between the hot gas and the steam bar. So let's see how to solve this numerical. So the diagram for this case is like this. So one of the fluid is flowing, that is hot gas is flowing from the left to the right, say the hot gases with a certain flow rate, while the cold gas is flowing counter current through the exchanger. And for this case, we want to know how many number of tubes we require in that situation. So if you see here, then we have a certain data with us, and the data is that, let's consider this is THR, the inside heat transfer the inlet temperature. This one is the outlet temperature of the hot liquid, the inlet temperature of cold liquid, and outlet temperature of the cold liquid. Also, they give the a mass flow rate of the hot gas and the mass flow rate of the cold gas. So with this and the certain data which is mentioned from that one, we try to calculate what is the number of tubes is required. The geometry is given. Here the diameter is given, diameter of the tube. Okay. Also, they give the length of the tube. The length of the tube is also given. Okay. And the length of the tube is also mentioned. And from that one, we try to calculate how much is the number of tubes is required. So let's see first what are the data is mentioned here. The data is like that. The steam, which we consider the cold one because it is absorb the heat from the hot gas. So steam inlet temperature of steam is given TCI 180 degrees Celsius. So this is we taken from here, that as here we have the data mentioned the steam enter at 180 degrees Celsius. So it is given the steam enters counterflow heat exchanger price at 10 bar. So at the 10 bar, the temperature of the steam is 180, and that's why we take the inlet temperature is this one and leaves at 350, which is the outlet temperature of this one. Also, the hot gas enters, so we take this 650 inlet temperature, and outlet temperature is as it is not mentioned. So with this one, let's see, we have data with us. Inlet temperature 180 degrees Celsius, outlet temperature 350 degrees Celsius. A mass flow rate of the steam is given 720 kg per minute. We need to convert into kg per second. Specific heat is given as 2.71 kJ per kg, convert into the joule per kg. And the H1, the heat transfer coefficient for the steam is 600. Same thing for the hot gas. We say it is a hot stream. Inlet temperature is given 650 as per the statement. Outlet temperature is not mentioned. Okay, so we are taken this is from the saturation one, but here it is not mentioned. The mass flow rate is given for the gas. We represent by mg. 1320 kilojoule, kg per minute, and the specific heat is given 1 kilojoule per kg K3. And also given the heat transfer coefficient for the hot gases is 250. So we consider that, and another data with us that are the diameter of the pipe is given and the length of the pipe. If you see here, then we can say that the one of the fluid, say hot liquid, is flowing through this tube and the cold liquid is flowing outside this one. So steam is flowing outside one and the hot liquid is flowing inside one. So accordingly, we have taken the data and we are writing this one. Okay. So now with this data, we try to get what is the how we can get the the number of tubes. So let's see. This is a statement, and from that statement, we already written the data, and now we try to see how we can solve that numerical. Okay, so let's try to solve that numerical and with us. So we want to know how many number of tubes be there, the value of n that we want to calculate. How I can calculate the n with the given data? Already we have the data with us, and the data is like that we have the temperatures, two temperatures, three temperatures with dimensions, mass flow rate, and the certain specific data, specific heat and the heat transfer coefficient. So let's first write down the formulas which is be here, how we can calculate the n. As we know that we can calculate the n if we know the surface area. If I know the surface area, then I can easily calculate the number of tubes with this formula. Okay. So in our statement, we have the data of T, we have the data of L. The pi value is constant. We do not know the surface area nor the I. So this we need to calculate. Okay. So if I know the value of surface area, then I can easily calculate the value of L. So how I get the value of A, surface area? Then we know the formula, a general formula with respect to the heat transfer by the convection. The Q is equals to the U into A into delta T out. So if I know the value of Q, if I know the value of U, if I know the value of this delta T ln, I can easily calculate this surface area, which is the this one. Which I can calculate. Okay, get it. Now, what is mentioned in our numerical? In our numerical, they mention the three temperatures. Okay, so let's first we try to get how I can get the value of Q. Okay, to calculate the Q, use the energy balance equation. Energy balance equation. What is that equation? The equation is that Q is equals to the M into specific heat into the temperature difference of the steam. Okay, either it is a cold one or it is a hot one. So here in this case, either it is a steam or it is a hot gases. So from that one, I can get the value of Q. As in our problem, we know the data of mass flow rate, we know the data of specific heat as well as the temperature difference. So I can easily calculate the energy balance equation. Okay, now focus on the U. How I calculate this U? This U value I can calculate if I know the formula 1 upon U is equals to the 1 upon H1, or we say the I, plus 1 upon H4. Okay, so either we can write 1 upon heat transfer coefficient for the stream plus heat transfer coefficient for the gas. Okay, so these two values with us, I can easily calculate the value of U. Okay, now this solve, so we can get a value of Q Okay, the Q value is okay for us. With this formula, I can get a value of Q. From this one U, I can get a value of U. Now let's focus on this delta TLM. How I can calculate the delta TLM? Now delta TLM is calculated on the basis of the formula that we have. Delta TLM is equals to the delta T1 minus delta T2, as this is a formula well known to us, upon the ln of delta T1 by delta T2. Now here we consider the certain conditions. And what are the conditions? The conditions are, this is the counter current flow. Counter current flow. So as it is a counter current flow, always we write the equation with that. How? Let's see. Let's consider the string. So let's see. This is a cold string with temperature TCR and TCO, inlet and outlet temperature. Okay. Similarly, for the hot liquid, I can take, say, the one of the fluid. This is THR and THO. Now, what is the delta T in this case? The delta T is that. So I can write the delta T is what? Delta T1 I can write. This is this minus this one. So this is delta T1 and this is delta T2. So we get the value of delta T1 and delta T2 from this equation, as the flow is counter current one. Okay. So I can get a value of delta TLM from this one. So once I know the value of delta TLM, once I know the value of U, once I know the value of Q, I can easily get a value of this A. Okay. So let's solve one by one and try to get the values of each and every one. So you can write that one. So first we try to solve Q1. So according to the energy balance equation, I can write the Q, and I'm taking for the steam as both the temperature mentioned to me. That's why it is easy. Q for the steam is equals to the mass flow rate of steam into the specific heat of steam into the temperature difference of the steam, and steam temperature is TCO minus TCR. Okay, so this is, I say, so let's see. First, the mass flow rate of the steam is mentioned, it is 720 kg per minute. So I convert it into kg per second for my convenience. Into the specific heat is mentioned 2.71, which is also in kilojoule per kg per degree Celsius. So I converted this into the joule per kg. It means, as this is mentioned, Cp value, which is 2.71 kilojoule per kg. Okay, so I'm just converting that one per Kelvin into the 2.71 into 10 raised to the power 3, that is joule per kg per Kelvin. Okay, so I'm just converting this is for specific heat of the steam. So I'm just taking this is, and the outlet temperature is 350 of the steam, and inlet temperature is 180, that is entry temperature. Okay, so once I do the calculation of this one, I solve that one, I got a value of mass flow rate of the steam, sorry, heat transfer rate for the steam is VAT. Okay, so this is the first thing that I got it. So I just highlight this part so that next time I need these values to know. Okay, after that one, we say that at a steady state condition, if I say the heat transfer at steady state condition, I can write the heat taken by the steam is equal to the heat given by the gas. Okay. So if this is the condition, and from that one, as I am interested to calculate the one of the temperature, because here the outlet temperature of the gas is not given to me. So I'm trying to calculate that one. So I'm writing the formula Q4G is equals to the mass flow rate of the gas into the specific heat of the gas into the temperature difference, that is inlet temperature of the hot gas minus outlet temperature of the hot gas. So just put up the values of this one, the mass flow rate of the gas, which is being 1320, which is given in kg per minute. We convert into kg per second. Specific heat is also mentioned here. It is in a kilojoule. That is 1 kilojoule per kg Kelvin. So convert this into the 1 to the power 3 joule per kg per Kelvin. So put up that values, Cp value 10 raised to the power 3 into the temperature difference that we need to calculate. So one of the temperature with us, and the temperature is out inlet temperature, which is be given 650 minus Tho. So as we say here, the Q of S is equals to the Q of G. So I'm taking the value of Q of S, which is from here. Okay. So once I equate this one, that is 55284 is equals to the 1320 divided by 60 multiplied by 10 raised to the power 3 into 650 minus Tho outlet temperature, that is unknown to us. So once I calculate that part, we got the value of Tho after solving all this one, which is 398, around the value is 398.7 in degree Celsius. So this is another term that is I required, because this one is useful to calculate the delta TLM, because for the delta TLM we require the four temperatures. Now the next focus is on delta TLM. So we try to get a value of delta TL. So for the formula, delta TLM is equals to the delta T1 minus delta T2 upon ln of delta T1 by delta T2. Already we mentioned in the last one that here we can get these values. Okay. So delta T1 we got from here and delta T2 here. So we use that one for this case. Now with this one we can easily get delta TLM value. Okay. So we use the same thing to calculate the delta TLM. Okay. So simple, you can just draw a diagram like this one, that you can just mention counter current flow. Okay. Mention the temperatures, hot liquid flow in, hot liquid cold, cold liquid in, and cold liquid out. So we have both the things at all the four temperatures with us. So what are the temperatures? So we just writing here at temperatures, that is the value of delta T1. So we say that this is the delta T1. So I can write delta T1 is equals to the, so I can say this one thing, just on the basis of the last formula that we have. So this is the formula. So delta T1 is what? So we can write delta T1 as delta T1 is equals to the THO minus TCI, and delta T2 is equals to the, this is THR minus, just one thing, just here we make mistake here. So we just do that part as, so I can write here the one flow is this one, say hot liquid flowing THI THO, and the cold liquid is flowing, that is TCI and TCO. Now this is the correct way that we can write, and now we can say this is delta T1. So here we can write delta T1 is equals to the inlet temperature of the hot liquid minus outlet temperature of the cold liquid, and delta T2 we can write from this one. Okay, so we are writing from here, that is outlet temperature of the hot liquid minus inlet temperature of the cold liquid. So with this one, we can easily calculate the value of delta T. So what is the value of THI, THO? So we have, so we can write as THI is 650 inlet temperature of the hot gas. Outlet temperature of the steam is 350. So it is 300, and THO, which is the we calculated, which is 398.70, minus inlet temperature of the steam is 180 degrees Celsius. So with this data, we can easily, so that is the delta T2. Okay, so it is around, say, 8, 1 into 108.70 degrees Celsius. So we just put up the value of delta T1 and delta T2 here, and we got the value of delta TLM, and delta TLM that we got is around delta TLM is equals to the 257. So this is the value of delta T. So this is my sorry. So according to the first case that we have the data of that what we calculated. We calculated the value of Q. We calculated, we calculate the value of delta TLM. Now focus on calculate the value of U. How we calculate the value of U? Again, you can write value of U, that we can calculate the value of U as putting this value here, 1 upon H, the heat transfer coefficient for the steam that we have 600, and for the gas is given 250. So on the basis as the data is mentioned here, okay, 250 and 600. So here 250, okay, and 300 we have. So we calculate that values accordingly, and so we writing that values as, and after solving this one, we got a value of U is equals to the 180 watt per meter square per cube. Okay, this is my third test. It means I got a value of Q, I got a value of U, it means I got a value of Q, I got a value of U, I got a value of delta TLM. Put all these value Q, U, and delta TLM here, and we get the answer of number of tubes. So we can write a formula again and put up that values. The Q is equals to the UA surface and delta TLM. Value of Q is with us, which is 5528400. Value of U that we calculated 180. Surface area to be calculated, and delta TLM value is 257 degrees Celsius. So from that one, we got value of surface area, and the value of surface area that we got, it is 119.50 meters square. And as this is the surface area is required for the condition. Now we are calculate number of tubes. So number of tubes formula is surface area is equals to the number of tubes into the pi into the d into the L. So surface area is 119.50. Number of tubes to be calculated. Pi value to be constant. The diameter is given 30 millimeter. So convert it into the meter and multiply by the L3. So from that one, we got a value of N is around 423. So we can say that we can say that for this heat duty, say for this heat duty for U180 and delta TLM 257, we require the area is 119, and for this case, if we have the diameter of tube is 30 millimeter and the length is 3 meter, for that one we require the 423 number of tubes in the exchanger. Thank you.